Tagolimot Jr. together with my partner Khiana Torres, and this is our final PID output. I will be explaining the source code and the execution of our program, and also I'll be showing to you the output of our program. So we will be solving the dining philosopher's problem using the semaphore and then mutex lock. So let me demonstrate our method in solving this problem. We have here our 5 philosophers in the table. These are chopsticks. Every philosopher has 1 chopstick. And then in order for a philosopher to eat, the philosopher will need to use the left and right chopstick, so 2 chopsticks. And then other chopstick or the neighbor philosopher cannot eat if the right or left neighbor is currently eating. So for example, we have the philosopher 1 is hungry. Philosopher 1 can only eat if this chopstick and then this chopstick are free or not being used by the other philosopher. So in our program, we've allowed the philosophers to eat by this way. So for example, the philosopher 1 can eat using this chopstick. Then the neighbors, philosopher 2 can wait. Then the philosopher 5 can wait until the philosopher 1 is done eating. And then if another philosopher is also hungry, and then the chopsticks are free, then philosopher 3, for example, can eat together with philosopher 1, but not at the same time. It has some delay, or it is running at sequence 2 in order for the philosophers stop accessing the resource or the food at the same time, because that is not good if both of the philosopher access the food at the same time. And then after the philosopher done eating, you can put the chopstick below and put the chopstick down, and then it is checking if its neighbor is hungry. For example, P1 is done eating, and then its neighbor P2, philosopher 2, is currently hungry, but the P5 is not hungry. Then it will prioritize its neighbor, prioritize the neighbor to eat, so that it will not starve, or no other philosopher can get its turn eating and replace another philosopher that is hungry. In that way, we can avoid starvation, and then also the program will work efficiently, and no philosopher will get hungry, and all can eat. So let's start with the code. So this is our code. We have here defining the left neighbor. So we have the left neighbor and the equation. We have the equation. This P is the index of the philosopher. For example, philosopher 1. So the index of philosopher 1 will be 0, because we will start the index start at 0. And then plus 4, so equals 4 modulo 5. Then the result will be 4. So it means that the left neighbor of P1 is P5, and the P5 has an index of 4, right? And then for the left neighbor, we have index of the philosopher plus 1 modulo 5. So for example, philosopher 1, index of 0 plus 1 modulo 5 equals 1. and then it means that the right neighbor of philosopher 1 is P2, because P2 is index of 1. So let's go to other variables. We have the thinking. So these are the state of the philosopher. So first you have the thinking state, then after they think, they will become hungry. Then after they get the chopsticks, they were allowed to eat the eating state. Also we have here the mutex blocks. So we have declared the mutex, we have the main mutex, so this is our main mutex, and then we have another 5 mutex, so this is array of mutex. PS, it means that every philosopher have its own mutex, so have its own lock, so that other philosopher cannot get their turn or cannot replace replace the queue of the philosophers that is wanting to eat and they're hungry. So we have the p state here. This variable holds the state of every philosopher because we have 5 integer, 5 array integer. And then also the p index, it means that these are the index of the philosopher. We have the first philosopher, 0 index, second 1, and then the third we have 2 index, index of 2. The fourth philosopher will have index of 3, and then the last will be index of 4. And also we have a total of 6 functions, including the thread and the main. We have the check function. Method check is the chopstick, the left or the right chopsticks, or the left neighbor and the right neighbor are not currently eating or eating. And then we have the eat function, will indicate that the philosopher is currently eating. Then the put down function, after the philosopher done eating, then we will put their chopstick down. And then also we have the pick up, so philosopher can pick up the chopstick, then check if they can eat, they're allowed to eat. So we have the thread function, and then our main function. So let's start with our main function. In this function, the program execution will start, right? Then we have our initializing our mutex. So this is our main mutex. It is initialized as 1. So it means if the mutex is initialized as 1, then it is unlocked because it is incremented by 1 or initialized as 1. So the semaphore is unlocked using this mutex. And then we have here the int a. This variable integer is used in our for loops. We have here our first for loop. The purpose of this for loop is to initialize our mutex and semaphore using the mutex of every philosopher. I've said it earlier that we have 5 mutex for every philosopher. So we are initializing it inside this for loop. So iterating as 5 times. So the mutex, all the 5 mutex will be initialized into. So you can see here 0. It means that these mutex are initialized as lock. So the philosopher cannot pass this semaphore because the mutex is initialized as lock. So it's not the same as this mutex. This mutex is initialized as 1. It means that it is unlocked. It is unlocked at the first state, so initial state. And then we have the p thread. So every philosopher has its own thread. So the philosophers are independent to each other, and also they can run simultaneously. They are independent, then every philosopher has its own process. Right? Then we have the for loop, also iterate as five times to create our threads. So we have to thread create, then creating our threads here, the thread function, this one, and also passing our thread, so this 5 threads, and then also the argument of the thread, we have the index of philosopher, so this p index. So as the creation of thread, and also it will pass the index of every philosopher, so that that thread, we can identify the thread, or we can identify who is the philosopher who's in the thread. So this for loop is just for joining the thread, so we can start every thread if you want. And then the initial state of the philosopher will be the thinking state. So every philosopher at the creation of the thread, the philosopher will be at thinking state. So we have indication here, philosopher, you have a placeholder of integer, so the index of the philosopher plus 1, so plus, for example, philosopher 1. So philosopher 1, you have the index of 0, so plus 1, so 1. The philosopher 1 is thinking, and then in this code, or this statement, is just to color the thinking, just to color the thinking font into, or just thinking word into do. So let's continue. Let's go to our thread. So as the thread create, the argument or the index of the philosopher will be passed inside this argument variable, and then we have inside our thread we have of infinite loop, because we have a while loop infinite because it's always true, and then the argument or the index of the philosopher will be passed into the integer variable. So the integer will initialize as the index of the philosopher. So after that, the program will sleep into 4 seconds. So the philosopher will wait 4 seconds and then go to the pickup function. So for example, I have here, these are the initial state of every philosopher. So philosopher 1, the semaphore of philosopher 1 is 0, it means lock. And then the state is thinking. So the same as the other philosopher, the semaphores are lock, and then their state is thinking. And then let's take the philosopher 1 as the example here. So let's say philosopher 1 goes to this function pickup. So let's go to this function. We have the index of the philosopher, so the index of philosopher 1 is 0, so the value of this p is 0. And then we have a semaphore wait here, so it means that if the mutex is unlocked, then the philosopher will pass this semaphore. So as we said earlier, that the main mutex is initialized as unlocked. So the first philosopher 1, can pass this. So by the way, it doesn't matter who is the philosopher came here first. Maybe in some cases philosopher 2 came first than the Philosopher 1. So it doesn't matter. So it's just an example. So let's take the Philosopher 1 as an example. So the Philosopher 1 can pass this semaphore and then lock it. So for example, Philosopher 2 is done sleeping in 4 seconds, and then also call this function back up, and then since the Philosopher 1 came first and then came this semaphore will be locked, and then the Philosopher 2 will wait and cannot pass this semaphore until the Philosopher 1 open the semaphore. So let's go. Philosopher 1 will equal to hungry state. After it passed the semaphore, it will be initialized into hungry state. So let's change the state of the Philosopher 1 into H. It means hungry. And then we have an indication here that the Philosopher is hungry, and also a color red. We color the font into red. Then after that, it will wait for 1 second and go to this function check. So the Philosopher 1 now, after it's wait, after it sleep for 1 second, and then it will go to this function check. And also the index of the Philosopher is being passed in the check function. So let's go to this function. This is our check function. Inside our check function, we have our p state. We have our condition, if condition. So let's evaluate our condition. So the p state of the current, if the p state of the current Philosopher, in our case Philosopher 1, is equal to hungry, so this is true, right? Because the state of the Philosopher 1 is hungry, so this is true. And so the p state of the left neighbor of Philosopher 1 is not equal to eating. So if the the left neighbor of the Philosopher 1 is not currently eating, so this is true, right? Because the left neighbor of Philosopher 1 is the Philosopher 5, because the table is round and see. So this is our Philosopher 1, then the left neighbor is Philosopher 5. So this is true because the left neighbor of Philosopher 1 is not currently eating, because Philosopher 5 is thinking. So this is true. And then the other condition, if the p state of the right neighbor of the Philosopher is not also not eating. So we have an example, Philosopher 1. So the right the right neighbor of the Philosopher 1 is Philosopher 2, and then the Philosopher 2 is not currently eating because Philosopher 2 is thinking. Philosopher 2 is waiting here, waiting in this semaphore, and then its state is not currently changed into hungry state. So at this time, the Philosopher 2 is in here waiting. So its state is not currently changed. Then because the condition is true, then the Philosopher 1 will came inside this condition. And now we've changed the state of the Philosopher 1 into eating, because as you can see here, the p state of the current Philosopher will be initialized into eating state. So let's change the state into eat, means eating. Then it will sleep for 2 seconds. Philosopher 1 will wait into here in this 2 seconds. And also we have indication that Philosopher placeholder integer picks chopstick, also integer, and integer means that Philosopher 1, so we have here 0 plus 1 is 1, so Philosopher 1 picks chopstick. We have here left plus 1, so the index of the left, so it's 4 plus 1, so 5, so chopstick 5, and then p plus 1 philosopher index is 0 because we have philosopher 1 plus 1, so equals to 1. So it means philosopher 1 picks chopstick 5, chopstick 5 and chopstick 1. So it is allowed to eat because philosopher 1 picks 2 chopsticks. And then we have our symbols. So it means that this semaphore uses the mutex of every philosopher. So in this case, the mutex of philosopher 1, since the semaphore of philosopher 1 is initialized to 0, and then we have a sympose here because we have all known that sympose means incrementing the mutex. So it means that unlocking the mutex. So we have here from 0 to 1. So now the semaphore of philosopher 1 is unlocked because we've incremented it to 1. So the semaphore of the first philosopher is unlocked. After that, the philosopher 1 will go back to pick up function. So in here, because we call the check function and it will return here. And also we have the sympose. It means that this is our main mutex, right? Main mutex, this mutex. And then we have the sympose. So we are unlocking the semaphore. So we're incrementing the mutex into 1. So now the sim weight is, or this mutex is unlocked. So as we remember that philosopher 2 is currently waiting here because the sim weight or the semaphore before is locked. So since philosopher 1 passed this sympose, this semaphore now is unlocked. So philosopher 2 will go inside. Let's continue now. Let's just continue for the philosopher 1 now. So let's continue with the philosopher 1 since after the philosopher 1 pass here, it will unlock this semaphore, right? Or this mutex. It will unlock this mutex, so other philosopher can now go inside in this line or in this statement of code. And now we have sim weight here. So we have a semaphore here, and then it is using the mutex of every philosopher. So since we have a philosopher 1 and this is the mutex of the philosopher 1, since the mutex of philosopher 1 is 1, it means this mutex is unlocked. So the semaphore here is also unlocked. Then if it is unlocked, then philosopher 1 can pass this semaphore, and then after passing this semaphore, it will change or decrement because it is same weight. Same weight is decrementing the mutex and sympose is incrementing the mutex. It means unlocking and locking. So now after the sim weight, it will lock or decrement this into it will decrement the mutex, thus locking the semaphore. So now philosopher 1 semaphore is now back to 0 or lock state. So after that, it will wait for 1 second and then go back to its own thread. So here the philosopher 1 will go back here, and then since it calls this function earlier, it will now go in here and then call this function. Now the philosopher 1 is will go here in this function and then indicate that philosopher 1 is eating. so it will wait in the 2 seconds. So let's assume that the Philosopher 1 will eat, and then the 2 seconds delay will not end yet. So let's go back to our pickup. As we remember, P2, the Philosopher 2, passed this mutex, right? Because the Philosopher 1 opened it here. So the Philosopher 2 came inside here and then locking the mutex again. And then since this is a semaphore wait, the other, for example, the next Philosopher that came after Philosopher 2 is Philosopher 3. So now the Philosopher 3 is also waiting here because Philosopher 2 is lock the mutex or lock the semaphore. So now the after the Philosopher 2 pass this semaphore, it will change the current state of Philosopher 2 into hungry state. So let's change it into H means hungry. Then it will indicate that Philosopher 2 is hungry, and it will go the same steps, the same step as the first Philosopher. Philosopher 1 will sleep and then go to the check function. After it goes to the check function, let's go to here, and then it will check the condition if P state of the current Philosopher is equal to hungry. So in our case, the Philosopher 2 is hungry, so this is true. And P state of the left neighbor is not currently eating. In this condition, it is true, right? Because Philosopher 2 state is equal to hungry. But in this condition, it is false. Why? Because the left neighbor of Philosopher 2 is the right. The left neighbor of Philosopher 2 is P1, right? And then P1, the current state of P1 is eating. So this condition is false. So it will not continue in this condition since this condition is false. Then it will not go inside this condition. So the current, it will not unlock the semaphore of Philosopher 2 because it cannot go inside in this condition because the left neighbor Philosopher 2, which is the Philosopher 1, is currently eating, so it will not go inside this function, and then it will not unlock its own semaphore. So it will go back here in this function, pickup function. It go back, then it came here and then go back here. So it will open the mutex again for another Philosopher. So this semaphore will open. So if the Philosopher 3 came after Philosopher 2 and wait inside, wait here, now it can move forward because the semaphore is open. So it will go here and then change the state into hungry. Stay hungry. So let's go back again to our Philosopher 2. So since Philosopher 2 opened this one, came open the semaphore, open the semaphore, it will go in this same way. So it seems the semaphore of Philosopher 2 is currently locked. The Philosopher 2 will wait here because its own semaphore is locked, right? Because it is equal to 0. So Philosopher 2 will wait and currently hungry. So now let's go back to our Philosopher 1 again. Let's say that the 2 seconds wait of Philosopher 1 is done. So it is done eating. So after this one, Philosopher 1 will go back to its own thread. So here, from here, and also will go back here. So after that function, Philosopher 1 will call this function, the pop down function. So it will put its own, let's go here, this evaluate this function. So we have also a sim wait here, mutex. So this mutex is currently also undocked. So the Philosopher 1 will go here and we change the state into thinking state, right? Let's change it to talk into T. It means thinking state. Now the Philosopher, it will indicate that the Philosopher 1 is put down the chopstick 5 and the chopstick 1. So it will stay, it will sleep, and then also it will indicate that the Philosopher 1 is currently thinking. And then we have the check function. So let's go first inside this function. So it passed the left neighbor as the index. So the left neighbor of P1 is P5. So let's go evaluate this one. So let's go to this function check. If P state, so the current state of P5 is equal to 100. As we have known that the P5 or the Philosopher 5 is currently thinking and it is not hungry yet. So this condition is false. So it will go back again inside this function, and then it will evaluate next the right neighbor. So let's go to the check function passing the index of the right neighbor. So the right neighbor of Philosopher 1 is Philosopher 2. So let's evaluate again. If the P state of Philosopher 2 of the current Philosopher, which is Philosopher 2, is equal to hungry, which is true, right? Hungry. And then the P state of left neighbor is not currently eating. So the left neighbor of Philosopher 2 is Philosopher 1. You can see. And then it's not currently eating because Philosopher 1 is currently eating. And the P state of the right neighbor of the Philosopher 2 is not eating. And then the right neighbor of Philosopher 2 is Philosopher 3. So Philosopher 3 is not currently eating. And then let's this condition is true. So this condition will come to true, and then now let's change the state of Philosopher 2 into eating. So as you can see, P state is eating and stay for 2 seconds, same as Philosopher 1, and then indicate here that Philosopher 2 is pick chopstick 1, and then chopstick 3. So same pose again. So now the semaphore of Philosopher 2 is incremented into 1, thus unlocking. The mutex of the Philosopher 1 increment into 1, thus unlocking the semaphore. So let's go back. So it will go back here. Go back. Let's go back here. So this now this the mutex will be unlocked, and then since the Philosopher 3 is can now pass into this function, I mean this semaphore, and then go into check again. But let's just continue with the current state of Philosopher 2. So since the semaphore Philosopher 2 is unlocked, then as we have known that Philosopher 2 is currently waiting here before, right? So now, since its semaphore is unlocked, it will pass this one and then go back to its own thread. Let's go back to its own thread here. So it came from the pickup function, then it will go back here and go to eating function. So it will go in this function and then indicate that Philosopher 2 is currently eating. So let's continue. Now the Philosopher 3 is currently hungry, right? Then it can now go to the check function, and then it will evaluate this if statement. So currently state hungry, true, and then the p states that the p state of the left neighbor, or the state of the left neighbor, is that currently eating this. The left neighbor of Philosopher 3 is 2, but Philosopher 2 is currently eating. So this condition will not be true, and then go back here. Then since the semaphore of Philosopher 3 is not unlocked yet, so let's change this one to 0 again. It's not unlocked yet. So the same happened to Philosopher 2. The Philosopher 3 will wait in this sim pose. Will wait. So let's try another what do you call it? Another case. So let's say that the thread that came after the Philosopher 3, or the Philosopher that came after Philosopher 3 is Philosopher 5. So let's take that case. So since this mutex or this semaphore has been unlocked by Philosopher 3 as, I mean, not this one. Since not this one. Let me go back again. Since the semaphore of Philosopher 3 has not been unlocked or not been incremented by 1, because the check condition is not true, the Philosopher 3 will go back here in this function, then it will open the semaphore of this mutex, because we have a sim pose here, and then the Philosopher 3 is currently waiting here. Let's say P3. Philosopher 3 is currently waiting because its mutex is locked, so it cannot pass. So let's take the case that P5 came after, or the Philosopher 5 came after Philosopher 3. So let's say it will pass here. P5 will change it to hungry state, so H. So it will the same as before. It will indicate sleep and go to the check function. Let's go to the check function. In our case here, we have the Philosopher 5. So if Philosopher 5 is equal to hungry, which is 2, and then the P state, or the left state, the state of the left neighbor of Philosopher 5 is not eating, so it's the left neighbor, it is Philosopher 4, and then it is true that it's not currently eating. This is true, right? This is true, and then the right neighbor of P5 or philosopher 5 is not currently eating, which is philosopher 1, and then philosopher 1 is not currently eating, and this condition will be true. The philosopher 5 will came inside this condition and then change the state into eating state. So now it will go inside. It will open its own semaphore, so it will increment into 1. So it will go back here. The philosopher 5 will go back to this pickup function and then pass this apex, thus unlocking this semaphore. So now let's say that philosopher 4 came after philosopher 5, so it will pass and then change state into hungry state. So now philosopher 5 is currently eating, right? Then open the semaphore of philosopher 5. Since the semaphore of philosopher 5 is currently equals to currently equals to 1, so it will pass here, pass this, and then go to eating. Go back to its own thread. Go back to its own thread and then go to eat function. Eat. So eat function and then indicate that the philosopher 5 is currently eating. So let's say that philosopher 2 is done eating. Here, came here and then back again, then go back to its own thread, and then go to the put down function. Let's say go to the put down function. So it will check, will it change to thinking state, then put down its port, then thinking state, then check if the left neighbor is hungry and is hungry. So as we have known that left neighbor philosopher to which philosopher 1 is not currently hungry, so it will pass this call and then go to this call. Then as we have known that philosopher 3 is hungry, let's evaluate this. Philosopher 3 is hungry, then its left neighbor, which is philosopher 2 is not currently eating, and then the right neighbor philosopher 3 is philosopher 4 that also is not currently eating. So it will go here and change the state into eating, and also indicate that it picks the chopsticks, and then now the from 0 into 1. So the mutex is unlocked, and then thus unlocking the semaphore. So since P3 is currently waiting here, and now its own semaphore is unlocked, so it will pass this semaphore and then go into 0. Go into 0 again, so lock again, then go back to its own thread, eating, and then this thing again. It will go over and over again. So all of the philosopher now can go. Next will be the philosopher 4 after the philosopher 5 done eating or put down the function. The philosopher 4 can now eat again, then same again. Philosopher 1 will be hungry again, and then next philosopher 2 will repeat. So as we have known that no philosopher has gone into starvation, because all the philosopher will be able to eat. Then let's run our program. So this is the output of our program. wait. Let me clear it first. So let's run again. So now the philosopher is thinking. Now the philosopher 3 is hungry. Then picks the chopstick 2 and 3. Philosopher 2 is hungry again. Hungry next to philosopher 3. Then philosopher 3 is eating. Philosopher 1 is hungry, picks 5 and 2. That's it. So it will repeat, and you can see that there are 2 philosophers currently eating. The philosopher are thinking, and then the is hungry again. So I think we've solved the tiny philosopher's problem using semaphore and mutex. So that is from our PAT output. Once again, I'm Marvin Tagolimot, and together with my partner Khiana Torres, this is our final PAT output. Thank you for watching.